And yeah, Suqi, do you want to share your slides?
Okay, so it's working now?
Yeah.
Okay, great.
Okay, so the next speaker we have Suqi Liu, who will talk about phase transitions in noisy high-dimensional random geometric graphs.
Okay, thanks for the introduction and thanks to the organizers. So thank you for having me here. So today I'll be talking about phase transition in noisy high-dimensional random geometric graphs. This is joint work with my advisor, Miklo Stretch. Random graphs have seen broad applications in real life, including social networks, wireless communications, and also in biological sciences. Among them, the most well-known model is probably the Erdős-Rényi graph. However, the independence of edges assumption is usually oversimplified. And in practice, people instead use random graphs with the latent geometric structure. So we start with some notations. Consider a graph denoted by a set of vertices and a set of edges. We denote the event I is connected to J if and only if there is an undirected edge between them. So the Erdős-Rényi graph GMP is simply defined as I is connected to J independently with the probability P. And the random geometric graph GMPD we consider here is defined as the follows. We first draw n independent random vectors uniformly distributed on a d-dimensional sphere. And I is connected to J if and only if the inner product between their underlying random vectors is greater or equal to a threshold, where the threshold is usually determined by setting the probability of having an edge to be equal to P. One note here is when people consider random graphs in dimension 2 and 3, in the literature, people usually study the Euclidean distance. However, it is more natural and convenient to study the inner product when we are in the high-dimensional space. So here we have the plots of two of those graphs. On the left, we have a random geometric graph in 2 dimensions. And on the right, we have an Erdős-Rényi graph with the positions borrowed from the previous graph. We can see they have distinct features within those two graphs. In a random geometric graph, there are more localized structures, while in the random Erdős-Rényi graph, the connections are more global. And also, in particular, the random geometric graph is abundant in triangles. So here I have 2 more graphs with their exact position removed. So now we're interested in the question, for a given graph, can we tell whether it is a sample from GMP or it is a sample from GMPD, which has an underlying geometric space? So the hypothesis testing problem is understood through the study of the total variation distance. This problem was first studied in the seminal work by Devroy et al. In 2011. So it showed that when a dimension goes to infinity, GMPD is indistinguishable from GMP in total variation distance sense. And later in 2016, Buback, Ding, Alden, and Raj actually pinpointed an exact order of dimension when the total variation distance transitions from 0 to 1. And in the regime where the total variation distance goes to 1, they actually provided a computationally efficient statistic which can tell the difference. In other words, GMPD goes through a phase transition at the dimension of order n to the cube. So in GMPD, the connection condition on the latent space is a deterministic function. However, in real life, a lot of connections have some stochastic behavior. And in general, we can consider this conditional probability to be a function over the inner product, where we call the function phi here the connection function. So in this work, we're particularly interested in the following question. How does the property of the connection function affect the dimension threshold in the phase transition phenomena? To this end, we study this particular family, one parameter family of connection functions phi q, which is defined as a convex combination between a constant p, which corresponds to the connection function of GMP, and the indicator function, which corresponds to the connection function of GMPD. So this connection function smoothly interpolates between GMP and GMPD. When Q equals 0, this corresponds to GMP, and when Q equals 1, this becomes gmpd. And we can view Q as controlling the geometry strength or the level of noise in the graph. So we denote this graph by gmpdq. There is actually another interpretation of gmpdq as an edgewise resample gmpd. So we first take a sample from gmpd. Then for each pair I and j, we flip a bias coin with heads probability q. If the coin shows heads, we keep the edge or non-edge in the graph. Otherwise, we resample the connection independently with probability p. So now this figure is a sample gmpdq, which is taken by combining the two previous graphs we have seen, where the black edges are those from the gmpd and the red edges are those from the Erdős-Rinne graph. So here are our main results. It is summarized as the following theorem. We consider P to be fixed between 0 and 1. That is, we're in the dense regime. So the impossibility of detection theorem says if NQ goes to 0 or N cube Q squared over D goes to 0, then the total variation distance goes to 0. On the other hand, if N cube Q to the 6 over D goes to infinity, then the total variation distance goes to 1. And in the special case of Q equal to 1, remember this corresponds to the GMPD, then the theorem recovers the results of Buback et al. Oops. So by choosing a convenient parameterization of the dimension and the noise level, we can actually depict a phase diagram in a two-dimensional space. Suppose that D grows as n to the alpha and Q approaches 0 as n to the minus beta for some alpha beta greater than 0. Then the previous theorem translates into the following phase diagram. So in the red region, the total variation distance converges to 0, which means detection is impossible. In the blue region, the total variation distance converges to 1, which means the detection is possible. And also we have an efficient algorithm to detect the geometry. And we also see there is a yellow region, which is not covered by the theorem. And the rest of the talk is devoted to proof sketches. So to begin with, we first state two rough bounds through two simple arguments on losing geometry. So first, when the dimension is much higher than n to the cube, recall the result by Buback et al. GMPD is asymptotically indistinguishable from GMP. So as an edgewise resampled version, GMPDQ is also indistinguishable from GMP. And if Q is decaying really fast at an order which is smaller than 1 over n squared, then by Markov's inequality, there is at least one edge that is sampled from GMPD is a smaller O1, which also implies detection is impossible. And those two previous rough bounds translates into a vertical line and a horizontal line in the phase diagram. And outside of the gray box is the region where detection is impossible. We can see that our results improves upon the upper bound in a large region. And also most importantly, it kind of points out a interplay between the dimension and noise level in this region. Okay, next we turn to the sketch of the impossibility results. I will be focusing on the interplay regime. So the first step is to convert the total variation distance between the distribution over two graphs into the total variation distance between random matrices through a data processing inequality. And the difficulty here when dealing with the connection function is that when we run another data processing inequality through this and upper bound this by the Wisher to GOE transition, the dependency over Q will be completely lost. So here we introduce a trick which is connected to the edge resampling argument before. So by this conditioning, we further can buffer bound the total variation distance by the total variation distance between a noisy Wisher distribution and GOE, and also some other distances corresponding to normalization threshold and so on. And in the next step, we translate the total variation distance into KL divergence through Pinsker inequality. So the benefit of resorting to KL divergence is the chain rule property. And by using the chain rule, we can further tensorize the matrix into vectors. And the rest of the remainder of the proof is basically several improved bounds on various quantities. So this concludes the proof for the impossibility result. Next, we turn to the possibility of detecting geometry. To start with, we ask the following question. What is the topological property of a graph that has an underlying geometric space? So consider two nodes with a common neighbor. What is the probability of them being connected to each other? So in GMP, because the independence of edges, this probability is P, which is independent of their location and other information. However, in a geometric graph, the connection is marginally higher than P because of the geometry. So this motivates us to consider just counting number of triangles in the graph, which is already witnessed by our observation that the geometric graph is abundant in triangles. However, we're doing something even smarter by using something called the Sine triangle statistic proposed in the original work of Buback et al. And the idea here is not only counting the triangles, but counting the centered version of the triangles. The reason for doing this is to reduce the variance. In GMP, by simple calculation, we can show that the expectation of the Sine triangle is 0, and the variance is of order n to the cube. And we have shown that in GMPDQ, the expected number of Sine triangle statistic is lower bounded by n cube q cube over square root d up to constant. And the variance is upper bounded by n squared n to the fourth q to the fourth over d up to a constant. And by simply using Shepard's inequality, we can show the total variation distance is lower bounded by something approaching 1 as n cube q to the 6 over d goes to infinity. This finished the detection regime. All right, I'll conclude the talk with two open problems. So the most immediate problem our result leaves open is what happens in the intermediate regime. That there even exists an intermediate phase where detection is information theoretically possible, while no efficient algorithms exist. The next question is, in general, how about other connection functions or underlying geometric spaces? Does the phase transition behavior trade-off of noise and dimension carries over to those more general cases? And thank you for your attention.
Maybe I'll ask the first question. Do you think either one of your bounds is sharp? Or?
Yeah, that's a great question. So that's kind of the thing that bothered us for a long time. And actually, we initially derived some other bounds, and then we keep improving it. Now this is the current bound we have. So first, let me talk about the lower bound on total variation distance or the upper bound on detection first. So this one is established using the Sine triangle statistic. So the next question we ask ourselves is, what about other statistics? So we went on to try other more general statistics, which are also considered by other people. For example, the signed cycles or signed cliques. And from the initial results we have, or from the hints we have by doing those computations, it seems like it's not possible to improve in this regime. And for the upper bound, that's probably where most of the things become loose because of the use of various inequalities. And there are several places where it can be loose. Firstly, because we use the convexity and also data processing inequality a lot. The second one is we use a lot of conditioning over so we translate a lot of conditioning over the entries into conditioning over matrices, and also the zero noise version. So that might also be the place where it becomes loose.
Oh, thanks. Any
Sure.
other questions?
So maybe in your first proof sketch, you mentioned some improved random matrix results. Can you comment on that? So what exactly the result is?
Yeah, so we made a couple of improvements so that to further get a better bounds. As I mentioned, initially we didn't get a good bound at this one. So there are two major improvements I have highlighted here. The first one is the expected negative log determinant of Wisha matrix. And this is an improvement over previous work by Eldam and McLenser. They consider a more general regime where it's a log concave measure, but we show that under the Gaussian assumption, we can actually improve both the upper bound of the order and also in the region where the bound works. And the next one is the difference between thresholds. This is an improvement over the original paper by Lugusi et al. By Dior Lugusi et al. And that improvement is over the difference between the thresholding, because when you're thresholding over the random geometric graph, it has dependency over both dimension and p. But when you're thresholding over the GOE, it's only a parameter which depends on p. So the difference of this one, we improve it from a smaller or 1 to square so we improve to from square root of something to that term itself. So which actually correspond to the convergence rate from the a beta distribution to a gamma distribution of the quantile function.
I see. Thanks.
Yeah, sure.
Any other questions? If not, I think we have a 10-minute break. So let's thank Suqi again and the other speakers in this session.